In this example, we have a very simple single loop circuit that contains only just a capacitor, some sort of a voltage source. No resistors, nothing else. Just a very simple application. And what we are being told is that V is actually a function of time. It's not constant DC. So it's 0 before 0 seconds, and then from 0 to 1 second it becomes like 4t. And then after 1 second it becomes this equation which contains an exponent in here. So what I have done is I went ahead and I just basically copied the equations of like how does the current relate to the voltage, how does the voltage relate to the current, and how do we compute the power and how do we compute the energy. And what we're being asked to compute is the current, basically this, the power, this one in here, and the energy here. So we're not being asked to compute the V because we were given that. It's a straightforward implementation of these particular equations. So for the sake of passive sign convention, I just want to make sure that you see it. So this one here is the same voltage, and the current that is flowing in here, I'm going to assume that this is the current I of t in here. And from the perspective of the capacitor, that current will be hitting the positive, so I'll be just using the positive throughout in terms of passive sign convention. All right, so let's get started. This capacitor is C is just simply, let me just write it in here, is 0.5 microfarads, or you can think about it as 0.5 10 to the negative 6 farads. All right, so how do we compute the I? Well, I'm just going to rewrite it here. It's going to be plus, because passive sign convention tells me that it should be plus, C times dV divided by dt. So all I have to do is just take the derivative of the voltage, and I have the voltage in here, and I have different ranges. So I'm going to tell you that I of t, we have different ranges. So what's the derivative of, well, let me just write it in here. It will be 0.5 times 10 to the negative 6, the derivative of 0, which is just simply 0. Okay, and that gives me 0, and that's for t is less than or equal to 0 seconds. Alright, so down the next range in here, let's focus on the voltage in here. So the voltage in here will be just simply C 0.5 times 10 to the negative 6, the derivative of that 4t. Well, the derivative of 4t in terms of t, let me just write it in here so that you can see it. dV in terms of dt is just simply d of 4 of t divided by dt, and that's just simply 4. So you can think about it as times 4, and that will be equal to the value, I believe it will be 2, and you can think about it as microamps, if you think about it in terms of units and whatnot. So it's half times 4, and then we have the 10 to the negative 6, so that's 10 microamps. And that's when the time is in between 0 seconds and 1 seconds. All right, so that leaves us with the last one, and the last one here is basically tells me that you have to multiply C, which is 0.5 10 to the negative 6, that's a C, times the derivative of d 4e to the negative t minus 1 in terms of time. So the way we do that is just simply the derivative of 4e to the negative t is just simply negative 4e to the negative t minus 1. That's basically it. We put it negative 4e to the negative t minus 1. Okay, and if we compute this particular equation in here, we'll end up with the following. Let me just do this computation in here. So if we just multiply it, we'll end up with, I believe it's very similar to the one before it. We'll end up with 2e, or actually negative 2e to the negative t minus 1, and that will be microamps. Let me just write this here. Okay, we'll do that. Let me just clean these equations in here, and you can scroll back the video just to see how I got them, but this is how it would look like. Okay, and we'll do this here and this one in here. Of course, that will be in microamps, and that's when t is greater than 1 second. So that's basically, we found the current. So we were asked to compute the current. We just found the equations for the currents. Okay, what else can we compute? Well, we can compute the power, and the power is straightforward implementation of just multiplying. It's just I times V. And just to see passive sign convention, again, I have to use the positive because the current is hitting the positive. Again, I'm focusing on the capacitor in here. So P is simply just a multiplication. So what is 0 times 0? Well, 0. So the power before time is 0 is just 0 seconds. Okay, what about if I multiply 4 times T times 2 here? And of course, we have to worry about the unit in terms of what this is microamps, so the result will be just simply 2 times 4, which is 8 of t, and this here will be microwatts, since the current is in micro, and that's basically when t is greater than 0 and less than or equal to 1 seconds. And the last one is just we have to multiply this equation with this equation in here, and what we get is negative 8 e to the negative, I believe, 2t minus 1. That's what it will be. Okay, and that's also microwatts, and that's for t is greater than or equal to 1 or greater than 1 seconds. Okay, and that will be the power equation. All right, what about the W, which is energy? So the W, if you think about it, it's just simply half CV squared. Well, I have to take a look at the V in here, so I'm just going to scroll out a little bit so that we can see it. All right, so it's half of CV squared. Well, V squared in here is just 0, so that here is 0. All right, so that leaves us with this one in here. What would V squared be? It will be 4t, and the both of them squared, and that will be half times C, which is 0.5. Okay, so I'm going to just say half. Well, it will be half times also half, which is 0.5 times 10 to the negative 6 times V squared, which is 4 squared times t squared. Well, 4 times t squared. Okay, so if you clean this equation, what you will end up with, I believe it will be 1/4, 0.25, and then of course we multiply times 4, that will go away because that's 1 divided by 4 times 4, so we'll get t squared times 10 to the negative 6, which is basically micro joules in here. So that's what we get. So let me just do that here, just rewrite it. Okay, so we'll get t squared microjoules. Or actually, let me just make sure it is half of C. Let me just make sure. It's half of C, which is also half times 10 to the negative 6 times V squared, and V happened to be 4t, so it's 4 times t and that whole thing squared. So that tells me it's 1 divided by 4 times actually 4 squared. So that square will go with this square. So we'll have a 4 in here. And then times 10 to the negative 6 times t squared. Okay, so it's 4t squared. This is of course for t is less than or equal to 0 seconds. And this is between 0 and 1. Okay, seconds. All right. What else? What we have? Well, we have the last range in here. So the last range is the following. It's again similar. I'm just going to do it in here so that I don't have to delete it and so forth. So it's half of CV squared, which is half times 10 to the negative 6 microfarads. That's where this is coming from, times 4 e to the negative t minus 1, and the whole thing squared. So that will be 1 divided by 4 times 10 to the negative 6, and that here will be 4 squared. So of course the square will go with the 4, e to the negative 2 times t minus 1. Okay, so that will become 4 e to the negative 2 t minus 1, and that's basically also microjoules because I'll get rid of that 10 to the negative 6, and that's when t is greater than 1 seconds. So we were able to compute the power, basically the power and the energy. All right, so let me just summarize these equations that we found. So I'm going to summarize them, and I'm going to do a little bit of plots in here so that we can see them. So the first plot I'm going to show you is actually what we were given is we were given this particular voltage. So the voltage across that capacitor, and just as a reminder, what we have is just a simple voltage source and a capacitor. That's what we have. And what we're looking at is the voltage across that capacitor in here. And that's basically plus minus V in here. And we're also looking at the I in here. So that voltage we were given, and it has different ranges. So before 0, I'm just not plotting it because everything is 0 before 0. So you'll see that the x-axis, which represent time in seconds, is just starting at 0 because everything before 0 is 0. And what you will see the following. We were given that it's 4t, and of course if it's a function of time, that's basically linear, and that's what you see in here. That's v of t, that's linear all the way up to, and as it turns out to be, it's 1 second. That's what we see in here. And after the 1 second, it's just exponentially decaying. So this is here is exponentially decaying, and it goes all the way to 0. Of course, when t goes to infinity, that voltage will go to 0. That's what we have in here. We were given this particular equation. Now what we did is we took basically the derivative of that v, we multiplied by this equation in here. Okay, we multiplied by c, and what we got is we got this equation in terms of the current, and this is how it looks like. So before 0 it's 0, after 0 it just happened to be that the current is 2 microamps. Okay, and after that we'll see that there will be a sudden jump in here in current, and then what we have is we have negative and also in here. So what we'll have is, because of the negative, we'll have an exponential increase in here until the I, of course, at infinity you will see that the I is also 0. All right, so something to pay attention to. So when I covered capacitors, I mentioned that the voltage cannot change instantaneously. And you can take a look in here. The voltage actually goes slowly all the way to 4 volts and then goes slowly down in here. You don't see jumps in voltages, but this doesn't apply to current. So current can actually jump across the capacitor, and that's okay. And that's what we see in here. It jumps from 2 all the way to -2. It's totally fine to jump, and it doesn't affect it. So current can jump, voltage cannot. All right, so more interestingly in here, so let me just focus on the power. So the power is just simply, we did the calculation. You can scroll back the video just to see the actual equations, and I just plotted them here. I just basically multiplied 0 times 0 is 0, 2 times 4t. What we did is we got a linear in here. That's basically the linear equation, and then a little bit of a jump in here and so forth. So I want to focus on that just so that we can interpret the results in here. So this one in here is actually, let me just draw it in red. This is basically the 0 line in here. So as you probably remember, when the P is greater than 0, we know that the element is actually consuming power. When the P is less than 0, we know that the element is given or releasing power. And this also applies to capacitors in here. So capacitors can have a P that is positive or negative. When it remembers, like it's an energy storage element. So what happens in here, as it turns out to be, that initially the P is positive. What's happening in here, it's consuming power. What's happening is actually it's storing that power, that energy. So that pulse of voltage that we get in here is just simply basically giving it enough juice so that it can actually store it, and that's what you see in here. We see that the power actually is stored, and you go all the way to 8 in here, and that's basically in terms, I believe it's micro. If I remember correctly, the power happened to be in microwatts in here. So this here, the unit has to be microwatts. Okay, perfect. Then what happens after these microwatts? Well, what happens is, like, we know that the current jumps because the voltage doesn't jump, and because the current jumps on the other side, we'll see that it's actually negative in here. What's happening, if it's negative, that means it's releasing that power that it actually consumed, and at the end, you'll see that it goes to 0. So that's exactly what's happening, and you can take a look at exactly how much energy it actually stored and released by looking at the actual work of the actual energy. So you'll see between 0 to 1 seconds, what happens is, and that's what you see, take a look at the equation, between 0 to 1 second, we provided it with 4 of t voltage, and the current that was generated was 2 microamps, and if you multiply them by each other and you compute it, you'll see the amount of energy that is stored is here, which is basically 4 microjoules. Okay, so that's 4 microjoules. Okay, well, it's 4 joules, but it's basically showing it to 10 to the -6. But anyway, and then after the 1 nanosecond, what happens, like the amount of energy stored in it goes all the way to 0, and you will see that it's pretty much the same. Now, if you want to see exactly the amount of energy that got stored, so what we can do is we can say, well, okay, let's compute the 0 to 1, the integral of the power in terms of dt from 0 to 1. Basically, let's integrate between here and here. I'm computing the area under this curve, basically, to figure out how much power or how much energy got given. That should give me this particular value, which is 4. So let's do this in here. What we do get is the power. Well, let me just compute with the power in here. So I'm going to copy this here because that's the thing we're integrating. Okay, we'll do copy in here, and look what we do. We'll do this one here. That's it. All right. So what I'm asking you to do is let's compute the integral of 8 of t dt from 0 to 1. So the integral, that should give me 8t squared divided by 2 from 0 to 1, and that's simply 4. And that's pretty much what we got in here, which is the 4 microjoules. Remember, this is microwatts, so we got 4 microjoules. So the area under the curve is 4 microjoules. Hopefully the area trapped in here, which should be negative because we're under the 0, should also be 4 because the amount of energy that we provided is the same amount of energy that it released. So we can double check that answer by saying, well, let's integrate from 1 all the way to infinity, p times dt, and that will give us the work, and that basically goes from 1 to infinity, -8 e to the -2 t minus 1, and that's dt. And hopefully you guys remember your integration, so you'll get -8 divided by -2 e to the -2 t minus 1, and that basically goes from 1 to plus infinity. And of course this will be 4, and I believe that will be 4, yes. And what we have is we have e to the -infinity minus e to the I believe 1 minus 1 is 0, so it's basically e to the power 0. You'll get 4, e to the -infinity is simply 0, minus 1, and that will be -4 microjoules, or microjoules, because that's exactly that. So it stored 4 microjoule initially, and it released 4 microjoules. That's what we see in here. That is what we see in this particular graph in here. So it went from 0 all the way to 1 second, it go to 4 microjoules, and it released that 4 microjoules.